Hello, in part number 5 we'll be looking into criteria of goodness of electric power systems. So criteria of goodness, such as for example efficiency, cost, weight, reliability and many others, are used for making decisions while designing systems. So why this particular design is better than some alternative design? So this decision should be taken by assessing criteria like the ones I mentioned before, and then the system design which shows better numbers for the criteria, better values of the criteria will be preferred, will be chosen. So this is the way we need to go, and this is what we will be looking into. So let's take a look at this slide. It looks a bit messy, but it is, I find it extremely helpful in the way of introducing criteria. What we see here are the variants of system designs for wind turbine drivetrains. So if we look from vertically, from top to the bottom, from upside to this direction, so we see we first have gearboxes, 3 stages, 1 or 2 stages, and direct drives. So this is the way how the system is built, what kind of gearbox is used, if it is used at all. In the horizontal direction, we see different electric generator types. So we start from an induction generator on the left hand side, and then further down double fat induction generator, and then electrically excited synchronous generator. And here we, on the right hand side, we have permanent magnet synchronous generators. So here on this slide we see how different gearboxes can be combined with different electric machines, with different generators. And you see that for each generator there are certain pros and contras. You see pluses are for pros and minuses are for contras. For some of the generators there are more information, for some generators a bit less. But the point is, all these combinations are feasible, and in real world all these combinations are being used today. So of course some combinations are more successful, more turbines are installed with this kind of a system, but still the point is they all are feasible and possible to use. And then this is the art of design, how to choose the best one from this variety. So we see that, for example, Siemens on this slide, they used induction generators with 3-stage gearboxes. It was probably some old design, so maybe this is not very modern, but it used to be quite popular. But also Siemens is, for example, here. So they use permanent magnet synchronous generators without any gearboxes, so it will be then direct drive. So the same company can actually use quite different topologies of the system, quite different designs of the drivetrains. And an engineer should be capable of navigating within this space of combinations of different components. And this is exactly what DriveConstructor will help you to learn, to master. So now to the criteria. COE, cost of energy, is quite normal criteria to use in all kinds of power generation applications. Should it be wind turbine, tidal turbine, hydro power station, or something similar to that. Cost of energy is an integral criteria because it includes many individual criteria into itself. So for example, you can see that efficiency is included here and availability. These 2 criteria are part of cost of energy. So I should probably explain a little bit how cost of energy is calculated. So on top here we have all costs associated with building and running the power station, wind park for example. So all costs, like cost of the turbine itself, and of course the generators and electric drives and transformers, whatever is inside the wind turbine, together with the cables and power station, connecting all power lines from individual turbines. So all this will cost to build, and also there will be costs associated with running this park, like maintenance of the components, repair, and so on. So CapEx, capital expenditures, these are all the costs, and OpEx, operational expenditures, this is the other part of the costs associated with operation after the wind park was built. At the bottom here we have all energy which will be produced throughout the lifetime of the wind park. So we see that efficiency of the components will play an important role here. So if our wind turbine generator is not efficient, then the park will produce less energy than it would have produced with a better generator. Availability is like a derivative of reliability. So availability says how a long time of the overall time of the existence of the system it is available for generating electricity. So if we look now to the bottom of this slide, we see this diagram which shows that many criteria, efficiency, availability, capital expenditures, and operational expenditures, they all feed into cost of energy. So they together make cost of energy as the integral criteria. And this individual criteria can be in contradiction to each other. So we see efficiency and availability is in contradiction, or efficiency and capital expenditures are in contradiction, these two criteria. What does it mean? For example, a very efficient generator will cost a lot. That means if we want to increase efficiency, we need to increase capital expenditures at the same time. So it is not guaranteed that we choose high efficiency for the power drive train, the cost of energy will be higher, because maybe the cost will be so high or will be lower. This is quite a complex picture, and of course you will see more when you work with DriveConstructor. So this is a little bit messy, but still probably a useful introduction into this question. Well, so on this slide we show even more complex picture than before. So I said that cost of energy is the criteria for judgment on goodness of the power generation plant solutions like wind or tidal turbine park. But actually it is not enough to have just cost of energy as the criteria. So many other additional criteria which you see here below also will play a certain role. So for example, IP status, it's intellectual property status. So if, for example, some special design of the drivetrain is patented by someone, which happens sometimes, then we simply cannot use this design without buying a license from the patent owner. So that means even though our cost of energy is lower than in the competitive design, but if we are not allowed to use it, it doesn't matter. So we have a showstopper here. Another issue is transportability. So if the say the blades are too long, the wind turbine rotor has too large diameter, probably we cannot transport the blades to the site at all, so there is no tracks available. So things like that should be taken into account. And we can see that, for example, here cost of energy is 50 and here it is 60, but still, because of the other factors than cost of energy, we see that this second design has lower cost of energy, and which is better than the first one. So this is the first one, this is the second one. So the picture is getting more complex, and actually in the real world we always should work with all these details, all these criteria and sub-criteria, and we can try to unite them into bigger integral criteria, and this is actually also the language the engineers are talking to each other, and they are talking to the management and to the potential customers and sub-suppliers. So you will have to learn how to deal with all these criteria. Now one example from a different industry, from maritime industry. So criteria here are quite different from what we had on the previous slide. So before we had cost of energy, which was the ratio of all costs to all energy produced. But here we can see that, for example, for ferries, we have emissions, CO2 emissions, divided by passengers transported. So emissions per year over passengers transported per year. Another criteria is a different kind of emissions divided by number of trips per year for the ferry. You can see that, for example, for cruises, here the criteria are somewhat similar, but now we take fuel used to sail over the average passenger cruise day. You see it here. So criteria can be quite different for different kinds of ferries. Mega yachts, here's maybe a little bit funny example, but they divide emissions per year by luxury space on the yacht. So it's quite a special case. So you see these criteria are quite different. And of course, when we are talking about power drivetrains, we need to see how our power drivetrain design is affecting these emissions, for example, or affecting the space on board. So if our propulsion system is bulky, if the electric machine and the electronics is so big that we do not have any space left on the vessel for like passengers or for putting goods there, that means we are making our criteria worse. So that means our power system is not competitive, because maybe our competitors have a more compact system than what we have. We continue with the marine systems and the criteria for marine systems. So you see the important criteria could be functionality of the system, just the propulsion system on board the vessel, for example. It should just turn the propeller and provide the movement. Functionality is the first one, cost is the second one, and environmental impact is the third one. So if we replace with our electric components something that was not as environmentally friendly, for example, we replacing diesel engine by electric machine, so then we improve this environmental impact. So on this criteria we win, but probably the cost will be higher. This could be the case. So again, like we did look into the cost of energy, we can look over the lifetime of the system. So you see that's horizontal. We have time here. And first, when building the propulsion system for marine vessel, we invest. This is CapEx, capital expenditures. And then after that, when the vessel goes in operation, when it sails, we have OpEx here. So the rest of the life is just OpEx. So we maintain the components, we repair them, and it costs. So it defines the cost. On top of that, we have, of course, cost of fuel. You see it here. And we have some overhauls and repairs. And also we have cost of not running. So when our vessel got failure in some of the system, it needs repair, it needs being in the dock, and then it is not earning money, it is not transporting anything. So then it is also costs associated with that. So what is the point here? We can first, for example, originally reduce CapEx, so have system designed with lower cost of these components, but the pay can be, for example, higher operational cost. You see, so there will be a trade-off. like in any design case. So you win something, you lose something. So designing a system is something like bulging a balloon. So you push it on one side and then it bulges out on the other side. Okay. Now one example from general industry. For example, some plant where we drive a pump or fan or conveyor with our motor. So if we look at the overall cost of having the system, it is called cost of ownership. So we can own the motor with the frequency converter and transformer for driving something. We can own it for 5, 10 or even 20 years before all these components just age and fail. So what is remarkable here, the cost of purchase. So initial money you invest in having these components can be quite low if we look at the lifetime cost of it. So it's just 1% or less what we pay upfront. But then we will have cost of running. It's usually for electric systems. It will be cost of electricity we consume and cost of repair and maintenance of the components. But also there will be cost of not running. So what does it mean? So if we are pumping, say, oil on the oil platform and our motor is out of operation, we lose money every single hour of non-production. It can be quite costly depending on the production nature of the production site or factory. So you see, this cost of not running will usually occur due to lower reliability of our components. So maybe our motor has protection which is not okay for this kind of environment. Maybe it's chemical factory or whatever, and maybe this chemical components are destroying our motor insulation or frame or bearings or whatever. So this can be quite costly, and this should be taken into account when designing the drive systems. Another quite typical example, just supporting the argumentation on the previous slide, that cost of having an electric system for driving a compressor. The cost may look like that if we take lifetime. So electricity is 81%, equipment cost, the motor and the electronics, is just 9%, and maintenance 9%. So what this picture is telling us, that efficiency of the motor can be quite important. So the cost saving from having high efficiency will be much more than we will save by just buying cheap motor in the beginning. So maybe if we buy a cheap motor, we sort of pay not 9 points but something like 5 points, but then electricity bill will be not 82 points but something like 95. So you see the point here. So examples like that are included into the exercises in DriveConstructor. We have seen that there is a wide variety of criteria, so many of them. But in DriveConstructor we focused on 4 most used criteria, which are cost, efficiency, space, and weight. So this will be enough, already enough complexity in the picture. And as I said, these 4 criteria are the most important. So we'll be looking into them in DriveConstructor. Another important aspect when designing power systems is how we place the components. So for example, in wind turbine, you see this picture is showing how much you can pack into the tower of the wind turbine. So you see it's uninterruptible power supplies here, and all kinds of electrical inverters, and control cabinet, and transformer, and a switch gear. So this picture here is showing how frequency converters can be placed inside the tower, so that we have a passage between them for the stuff, and we have them connected to each other from top. Sometimes transformers or electronics can be put on the tower of wind turbine instead of pushing them into the tower. So this is quite an interesting design topic. So putting the common components together so they fit the space and there's a good connection electrically between them, and so on. And one more example of how the equipment can be placed. So for example, we can use a container instead of using the factory space. We can put it outside in the container, and then we can have a transformer and some electronics here and some other units. I don't know actually what it is. Could be some heat exchanger or some control elements. So some nice examples from ABB here on having electronics inside the container. And this India team example is good because we see that some equipment is inside this container, but the transformer is put outside. So that means probably there was no space inside the container for this transformer, but they had to make it with high IP degree, with high weather protection degree, and then it was possible to just put it outside of the container.